Okay, this week we're going to talk about software applications and architecture, or software architecture and applications as I have it written. So let's proceed to the first slide and look at exactly what I'm talking about here. So right here we have kind of a sample software architecture diagram where just to in general get the feel that there's a lot of stuff going on with software and how you design software for it to be uh, uh, reusable, different components so that they can be reused in different places, which is kind of the quote unquote holy grail of software development and design, if you will. It's being able to develop components that are reusable. We'll talk a little bit more about that later. So, in this slide, let's talk about with the overview. We're going to talk about different types of software. And so, with respect to system software, application software, utilities, and how software is designed and developed will be another topic that we talk about. We'll also talk about make versus buy and modify. Do you buy software? Do you build it from scratch? Do you buy it and then modify it? Do you do things, do you do that with open source or closed source? We'll talk a bunch about, those different types of decisions that you have to make. So we'll also talk about programming, how software actually gets built. And within programming, we'll talk about compilation, how it goes from something that you write, something that's logical, kind of structured English, to how it becomes something that's executable by a computer. We'll talk about a little bit what I alluded to before, the notion of abstraction and reusability, and kind of the idea of how layering works in software. And we'll talk about open sourced versus closed source software and exactly what that means. And then the last thing we'll talk about is software tools, or I think this is the next to last thing. And then we'll talk about software testing. And we'll conclude the presentation with a look at testing and quality assurance. So this is this is the tip of the iceberg with respect to how software architecture and applications are done. And the goal of this is just to give you a very high level overview of what goes on a little bit underneath the hood with respect to how people design and develop software. So let's proceed on to the next slide here. So types of software. The first is application software. The second is what we refer to as system software, which has operating systems and device drivers. And then the next type of software are programming tools, debuggers, integrated development environments. And so we'll talk about these three bullet points: application software, system software, and programming tools. And then there's one more, which we're not going to talk about. I'll just give you a quick summary. And that's malware or malicious software, which is software that isn't supposed to be there and doesn't do the most integratable of things. We're not going to spend too much time on that. We might talk about that a little bit later as we discuss more security-related issues later in the semester. But we're just going to talk about different types of software that you intend to have on your machine, and that you intend to use, not stuff that you don't intend to use. We'll just limit it to that discussion for now. So moving on to the next slide with respect to system software. So system software is designed to operate the computer's hardware. It provides a platform for running application software, and application software interfaces with the operating system through what we refer to as an application programming interface. This includes the following types of software. It includes operating systems, device drivers, and basic system utilities. So, looking at this as a whole, system software is about it's about operating computer hardware and the different levels at which that happens. At lower levels, with respect to just components within your computer, such as your network card, your hard drive, your display, you have device drivers, which provide provide an abstraction layer, for the operating system and anybody who intends to interface with these actual devices. It provides an abstraction layer that just says, go for, if it's a display, for example, go display, this image, and doesn't involve you with the details of the pixels and the dimensions and all these different very intricate things as it relates to the device itself. It provides an abstraction layer that basically just says, go do this, and it does it for you. And so that's kind of, as we're alluding to this idea of layering that I've spoken about. Device drivers, allow you to interface with a device, allow an operating system or an application to interface with a device, but also abstract a lot of the details for how you need to go about doing that, while also giving you a pretty good level of customizability. So striking that balance. And then the other one is the operating system, of course, which is responsible for controlling all the different hardware, peripheral to your computer, like a display, a printer, or stuff that's inside the computer. Most importantly, the CPU, the central processing unit, and disk drives and network cards and things like that. And then what you also have is basic system utilities. Things that are meant to help you optimize hardware. So this is our overview of what system software means. So now, let's take a look at the operating system, the first piece of system software. The operating system, is basically software that manages computer hardware resources. It's responsible for input-output management, and what I mean for that is, when I think of devices that provide input and output, such as a mouse or a trackpad. You enter something and something happens on the display. There's input and output there. Keyboards, you once again you input something by a keyboard and you receive an output on a display. Disk drive, you can fetch stuff from a disk drive and write to a disk drive. So that's that's a very basic example of but maybe the most prime example of what an input-output device is a hard disk or even a USB drive. It's an input-output device because you can read and write to it. And then also a display, which is mainly responsible for output, but like I've been alluding to, the operating system maintains the input from other things and negotiates the output, to a display or wherever else it needs to go. So the input and output might not necessarily come from a single device. It might go in one, and something might come out through another. And the operating system manages that. Another important thing that an operating system does is memory allocation. And when I talk about memory, I'm really talking about what I referred to in the last lecture as volatile memory. Memory that when you turn your computer off, it usually does not retain that information at all. There are some exceptions to that. For example, the laptop that I'm doing this presentation on right now does actually keep power going at a very, very low rate, just so that some things can remain in random access memory, in RAM, or in just volatile memory in general. So getting back to the operating system stuff, memory allocation is a very, very important function. And with that, we're talking about random access memory, RAM, read-only memory, ROM, CPU registers. If you remember from the last lecture, we talked about registers as being those little tiny places of memory that are really close to the processor, so it allows the processor to read and write to those things really, really fast. So kind of the closest thing possible to the processor is usually your CPU registers. And then maybe one level removed is L1, L2, or L3 cache, like level 1, level 2, or level 3 cache, depending on, the processor architecture. There's a lot of processors are becoming augmented with different levels of cache these days. So you have additional space beyond those CPU registers, which actually sit on the CPU itself. So CPUs get smaller. They want to be more optimized for processing. There's only so much space to do things, so they augment it with forms of cache, so they can do stuff really, really fast. If you remember from the last lecture, of course. And then at the core of the operating system is the kernel. And the kernel is the program code that really manages the CPU, memory, and devices. I mean, that's the core of everything. It really is in the kernel. And in many cases, even in today's operating systems, the kernel is actually really, really small. For many, many years, and this may even still be the case, you could still fit the Linux kernel on a single 3 by 3.5 inch floppy disk drive, which I know that's archaic to you guys, but you could still fit it on a 3.5 inch floppy disk, which only has a few hundred K of memory. So it's very, very basic. And then there's all sorts of kind of applications that are directly related to the negotiation of hardware, which comprise the operating system as a whole. So that's why when you upgrade your operating system, it's a big deal. It's the kernel's not a big deal, but all the different device drivers and utilities and things that are really responsible for hardware management and optimization and things like that. That's what makes the operating system a really, really big part of your computer, or occupies a lot of space on your computer's hard drive. So it's also important to understand that computer hardware also has software, right? Like we talked about the CPU, for example, and which is just a piece of hardware, but also has very, very kind of low-level software that we refer to as firmware that's exclusively responsible for managing that resource. And again, a processor has something, the firmware has something very similar to an application programming interface. In kind of getting back to this idea of layering and abstraction, it's got a programming interface where the operating system, works with that, interface contract, if you will, a contract for how the computer hardware is supposed to interact or is supposed to react when you give it a predefined set of commands. That's exclusively responsible for managing that device. So just to give you an idea of that software exists at very, very low levels, and kind of at the lowest level we call that firmware, and exists all the way up to operating systems and application software. So many, many different levels of software, if you will. So let's go on to the next slide here and give you a summary of operating systems functions, just to give you a list of things. So the first thing is kernel operations, right? What we talked about before as being the core of the operating system. Something else is program execution, where rules are established via application programming interfaces that declare how programs are run, right? It's just kind of a contract, if you will, that sets the boundary conditions for when you give something a set of commands to how it's supposed to react. Another very, very important function for operating systems is this notion of hardware interrupts, which basically is a signal to the processor emitted by hardware indicating an event needs immediate attention. I'll give you a good example. When you press a key on a keyboard, you want that to immediately appear on the display. Every once in a while, your computer will get bogged down and it doesn't, but most of the time, it appears on that display. And that's because your keyboard is sending a hardware interrupt to the processor to process that event and output it to a display. That's exactly what's happening. Another important function is modes of operation, different levels at which people can access system resources. For example, there's supervisor mode or root, which is kind of like your, ultimate access. And then there's other levels or protected modes where you can only access certain things and other things may be off limits, such as if I log in as the root user versus if I log in as Matt Levy on my own laptop, I may have access to very different things. Um, Another operating system function is memory management, which is basically the management of random access memory. So when we talk about memory in this context, we're talking about RAM. It also another operating system's function is the management of virtual memory, which helps us basically allocate memory efficiently. It basically what it does is map virtual addresses, or kind of artificial addresses, if you will, to physical addresses, and allows us to store more than one thing at a particular physical address. This helps us use our available RAM more efficiently. So you may have also heard of virtual memory as a function of when you can actually allocate some of your hard drive or some of your actual hard disk to act as random access memory, which is good to some degree, but it does make it is way slower. So another operating system function is multitasking. And this allows computing operations to be run simultaneously. So we can be browsing the web, loading a web page, and checking our email in another browser tab. This is effectively a realization of multitasking. Another operating system function is disk and file access. We've talked about that. Device driver management is another one. Networking, how the operating system actually manages networking resources, the network interface card, the communications channels that are coming in and out of your computer, such as Bluetooth, TCP/IP, your regular internet connection, all those different types of ways that we communicate. Some computers have infrared, for example. So it's responsible for managing that networking function as well. Security is another one. The operating system is ultimately responsible for making sure that data stays separate as needed, and that you can only access certain things when you have the appropriate rights. And then the last function that I have listed here is management of the user interface. The operating system, many times sets the boundaries for what you can do with the user interface. For example, if you use, the OS X native interface, you're going to get the look and feel of the Mac operating system. If you tell the operating system to create a window, it's going to have that grayish kind of brushed aluminum type look to it that you commonly see with OS X. And the operating system is responsible for giving that to us, for allowing a software engineer, for example, to develop that and have the interface rendered in such a way. So then if, for example, if OS X changes the way they want those windows to look because they want to improve the look and feel of things, then if the software engineer is doing things correctly, are doing things in line with the operating system, they'll reap the benefits of those improvements. So now let's take a quick look at device drivers and what exactly that means. Usually there's one driver for each device. There's one driver for a keyboard, one driver for a hard disk, or one driver for a display or a mouse. Device drivers also, they operate as a device attached to a computer. They're usually attached in some way. And these device drivers allow access to hardware functions without needing to know the specifics of the hardware. So this is kind of, with these next two bullet points, kind of hammering home the details of what I talked about in some previous slides. Device drivers allow an application programmer to use hardware in a generic sense without needing to know about exactly what's going on underneath the hood. Because as an application programmer, I don't want to know all that stuff. I just want to be able to tell the device driver to do what I want it to do. Now I have to follow the terms and conditions of their interface contract or their application programming interface. I have to obey the rules and I have to program it correctly. But I don't want to know all of the details of exactly how that happens. I just want to know that if I, for example, tell something to be output to a display in 24-point font, that it will calculate the correct number of pixels, and I won't have to worry about that. I know it will render in 24-point font. So, just to give you another example, imagine how hard it would be if a programmer needed to know these exact details. I would have to calculate pixels, I would have to calculate all these different um, low-level details just to be able to do my job. We have this idea of layering in software development so that you don't have to know every single detail all the way down to the device. And so device drivers, like I've said, device drivers abstract the details from the application developer. And this notion of abstraction and layering, I'm just kind of hammering it home here, this notion of device drivers abstracting the details from the application developer, and in general, this idea of abstraction is a very, very important concept to computer programming, software development, software engineering, whatever you want to call it. This idea of abstraction, and I use the term also layering as something synonymous with abstraction. So now let's go and talk about maintenance and monitoring utilities. So system software is basically there to help configure, analyze, optimize, or maintain a computer. This is what maintenance and monitoring utilities are in general there to do. It can be thought of as an application software with hardware-focused functions. Because, for example, I have a disk utility on my, in the utilities folder on my, for my Mac, and I can, do stuff to my hard drive. I can partition it. I can optimize it. I can clean up, space that's not being used efficiently. It's just software there to help optimize my computing functions. And sometimes that can be something that is done automatically, or it can be something that a user needs to go in and do. So, it focuses on how the computer infrastructure operates and helps us optimize that. Usually to do it, you have to have a little bit of technical knowledge. You have to know, for example, what disk partitioning actually is. You have to know what different optimization functions do. So I provide some examples there. Disk compression utilities, antivirus software, disk space analyzers, and memory testers. Those can all be examples of maintenance and monitoring utilities. Once again, system software to help configure, analyze, and optimize or maintain a computer. That's what it's all about. So let's go to the next slide here and talk about application software. So application software is basically computer software that allows a computer to perform useful tasks to a human beyond the hardware, separate from the utility stuff. What do we need to do our jobs? Business productivity improvement, things like that. IT is an enabler of work functions. We've talked about stuff like that in class. And so many times, this has business applications, allows us to access content, content access software such as a web browser, entertainment software such as video games, and enterprise software such as a database management system can also be considered application software. And then another example I give is educational software. So, there's many, many other examples and subtypes to these examples, but I just provide a couple examples of what application software is to contrast it with system software so that you can understand the difference that system software is about the hardware and application software is, this is kind of almost sounds cliche-ish, about the human, where it's there to help the end user, to help us. So now let's take a look at how this stuff is actually developed. Let's get a little bit of a feel of what goes on underneath the hood with respect to systems and software development. So the first thing we'll talk about is closed source software, which is also called proprietary or commercial off-the-shelf software. This is basically a black box. You buy the software, it comes in executable form, and you use it for your own personal purposes or you employ. Microsoft Office 2013 is an example of closed source software. You can't look at the source code for that software. So basically, it's licensed under the legal right of the developer or the copyright holder. And like I said, it's compiled. You have no access to that source code. It's usually not able to be redistributed. However, closed source software can also be shareware or freeware, which does allow for redistribution, and in that case, they don't care. But the ultimate definition of closed source software is software where you cannot look at the source code. And then the implications of that, are many times in the licensing. So now let's look at the converse of closed source software, and that's open source software. And so, open source software is software code that's made freely available to the public. It has relaxed or non-existent copyright restrictions. And I put this quote in there to kind of talk about some of the advantages of open source software. There's, conflicting viewpoints as to what it produces better quality software. Closed source, where you have people, a certain number of people exclusively dedicated to focusing on making that software as good as possible. And then you've got this notion of open source software, where the software repository is public and anybody can contribute to the quality or development of that software. And so I put this quote in here, and this is a quote from The Cathedral and the Bazaar by a guy by the name of Eric S. Raymond, who's very popular in the open source community and really kind of one of the founding fathers of the open source community or open source initiative. And so the quote is, "Given enough eyeballs, all bugs are shallow." And what that basically means is the more widely available software is for public testing, scrutiny, and experimentation, the more rapidly you can discover all forms of bugs. So, the contention is made that you can produce better quality software faster if it's open source. Now, that is highly dependent on having a vibrant developer and user community, but that's another issue. But yes, that is certainly an issue, but the argument there is quite valid in many ways. Apache is the largest web application framework on the internet today. The largest the most widely used web server on the internet is Apache. It's open source. It continues to be a stalwart that allows us to do great things with the internet. And many other examples as well. Linux, Unix, all these operating systems are open source and have been so since their inception. The operating system I'm using right now, Mac OS X. A lot of people don't know this, but OS X actually runs FreeBSD Unix, which is a certain flavor of Unix, as the core of their operating system. So anybody who uses a Mac is using an open source operating system that was taken by, of course, Apple and modified in a number of different ways. But then also, while some of that stuff remains proprietary to Apple, they've also released a lot of their modifications back into the open source community. So let's talk a little bit more about open source software. And let's talk about some patterns that we find in open source software development that is kind of different from closed source. And I think it makes for a very interesting community and a very interesting way to produce software. The first is that users should be, and many times are, treated as co-developers. The users are every bit as important as the developer, and they offer a feedback loop between the person who writes code and the person who's using the software in many ways. And sometimes, many times, actually, the user and the developer can be the same person or be within the same community. Another pattern that's found in open source software development is this notion of release early and release often. We see this all the time in our lives as we exist on the internet. For example, a lot of the code that Google produces is open source. A lot of the code in Gmail, of course, it's web-based, so you can always see it, but you can also have access to their repositories. And so, if you notice, there's always new updates coming, and they come really quickly. It's not that there's a release once a year, or things go from Microsoft 2000, from, for example, Microsoft 2010 to 2013. There's a few years between major releases. In contrast, a lot of open source software is released early and often. Get something out to people that you think is free of most defects. There might be some things that were overlooked, that's inevitable. But if you can get it to a certain threshold, you can get it to people and get the masses using it so you can get feedback quicker. So that's one thing, another component is release early, release often. And along those lines is frequent integration. So they're not just developing components in isolation and testing those components in isolation. They're integrating them, sometimes on an hourly or daily basis, back into the main source, source code repository, and running tests on those things all the time, continuously, so that people know if anything breaks. And a lot of times what can happen in software development is that you fix one thing on one end of the software code base, and then it breaks something that seems so seemingly unrelated, but it is. And a lot of times that gets back to the fact that a lot of things are greatly reusable between different software components. So you can cause all different types of unintended effects, making software development a very complex practice. Another pattern that you find in open source software development is that there's usually more than one version. There's a developer version and a release version. If you want something more stable, you will wait for a release version, which doesn't come as frequently. But if you want the latest features, access to the latest things that are being worked on in the code base, you can download a developer version. But then you potentially also assume some risk because it could be a little bit buggier. Another pattern found in open source software development is that you have very high degrees of modularization. And what that basically means is that components are worked on and tested in isolation, but are constantly integrated. And those components, it helps separate concerns, separate problem space, so that people can work on something such as networking communications without having to worry about displays, for example, or what's displayed. So these components are worked on in isolation and tested in isolation. And I've used this term interface contract. There's effectively an interface between these components and other components to interact with one another and integrate and work together as kind of a team of software components, if you will, to produce an end-user application. And then the last pattern we have that's found in open source software development is a dynamic decision-making structure. And this usually just has to do with how humans are working on these things. There's usually governance. There's people who have certain rights to do things with respect to the software code. And then there's others who have to gather some recognition. Those are the people who actually have to spend time working on lower level things, or maybe more boring or rudimentary things, to become part of the development team and gain some credibility, so they can become better developers themselves and know the product better that they're working on developing. And so I have a statistic here that talks a little bit about how open source software development teams work, and that data suggests that some of these open source software teams I talked about are not as democratic as what was stated in this Cathedral and the Bazaar thing that we talked about. Open source software is not quite as some 15, 20 years ago, where it's not as democratic as the Bazaar model suggests, which we've been talking about with respect to how open source software works. And then an analysis of 5 billion bytes of free and open source code by almost 32,000 developers shows that 74% of the code was written by the most active of 10% of authors. So there's a hierarchy there. And inevitably, you have to prove that you have some credibility with the open source community before you can begin working on the most widely used things, such as the Linux kernel, for example. There's a very elite group of software developers who maintain that code base. And so, uh, along those lines of that statistic, the average number of authors involved in a project was 5.1, with the median at 2. So, most of these open source software development teams and components that are uh, out there in the world that you could potentially work on, they're usually very small teams. So let's go to the next slide here, and let's talk about the notion of make versus buy versus buy and modify. There's a number of different permutations to how you can do this, but let's just talk about kind of the overall theme of what this means. This is a frequent problem in IS decision making. Should you buy closed source software and integrate it into your business? Should you develop it from scratch? Or should you buy closed source software with the ability to integrate it with other software developed in-house vis-a-vis an API or application programming interface? Or should you download open source software, implement and modify it to align with your ultimate business problem? What I'm getting at here is there's a number of different ways to skin this cat. There are many things that have to do with the actual business solution or the business problem so that you can use technology properly and efficiently to develop something as quick as possible, but also having the desired qualities that are needed. So this is very difficult, and really it depends on the business and the business problem. So just something for you to think about, and let's recap it. Do you buy closed source software and integrate it with your business? Do you develop it all from scratch? Do you buy closed source software with the ability to integrate it with other software developed in-house? Or do you download open source software and implement and modify it? These are things that, as a decision maker of how to employ information technology resources, you have to consider. So let's get into the nuts and bolts a bit of how software is actually developed. How is it actually developed? What are the processes for how we get our applications? What are people doing to make all this cool stuff happen? So let's take a look at a few things. Let's take a look at the architecture and design of software and give you a beginner's look at design and architectural patterns. Let's take a look at computer programming, how software is compiled, what that means, developer tools that enable software developers to do their jobs. And this thing that I've been alluding to the entire time is this notion of application programming interfaces. And I didn't want to put a whole slide on it up front because I wanted us to talk about that in respect to software development. But once again, we've been talking about this notion of abstraction and layering with software components that is critical to how people interact at different levels of software development. So some other things we'll talk about is testing, quality assurance, and validation and verification. The different ways that you make software perform to be relatively bug-free and to satisfy user requirements or what the user wants. So let's go to the next software and talk about software architecture and design. And what this basically is are high-level structures of a software system. So some generic themes here. Software architecture has to support a number of different stakeholders, right? I mean, that has to be the design of software, how you diagram all these different components. You have to think about all these stakeholders, business managers, owners, users, operators. Another thing is there has to be, what I've alluded to a little bit, is separation of concerns. For example, it has to be fault tolerant, backwardly compatible, extensible, reliable, maintainable, available, secure, and usable, right? So, you have to be able to develop components that have these qualities, and you separate your concerns so that you don't have to focus on fault tolerance, backward compatibility, extensibility, reliability, maintainability, availability, security, usability for the entire application. You work on doing that for particular components, and then the hope is that the whole is greater than the sum of its parts, right? So that when you integrate those things, you still have those qualities. Some other generic themes are recurring styles and the notion of patterns, architectural patterns, design patterns. And then another one is conceptual integrity. You also need to have a defined vision that actually guides implementation. So let's take a look at this next slide and talk about patterns found in software architecture. So I derived these from Patterns of Enterprise Application Architecture, which is a book that I've read many times by a guy by the name of Martin Fowler, who is really one of the utmost experts on how to develop software code efficiently, and has really made it his life's work. He's very famous in software communities, just absolutely revered as someone who's been on the leading edge of, getting people to, work, showing people how to work in teams, how to develop software so that it has less bugs, operates more efficiently, while still keeping the end user goals in mind. So I'll give you some examples of patterns that are found in software applications. One example is domain logic, and what that basically means is separate logic and programming code into a specific to a business from things that can be reused elsewhere. So what that means is that a lot of times in software, you're going to have things that are focused on stuff that's more low level, such as how to interact with a database, or or sending and receiving, stuff onto the internet. Sending and receiving messages to some other interface or website or something that's going on. So that stuff, those are components in and of themselves. And so what domain logic patterns means is, when I talk about accessing a database, that's a domain. Database access, that's the domain. You're worried exclusively about building great software that has all these great components we talked about in the last slide for that specific domain. Then you have another one for communications, input output, and then another one, which is kind of related to the text here on this slide, related specifically to business logic, things that have to do with the business problem that you're trying to solve. Isolate those things. Isolate that code so that business logic doesn't pervade throughout the entire application. Separate those concerns. Separate those things into components so that they can be reused and modified, and it's easier to find bugs. As opposed to when you have things that are proliferated all around the software, it becomes very, very difficult to find what you're looking for. Another theme or another pattern is a data source architectural pattern. Along those same lines, separate programming code that references a specific data source via an API that can be reused. Once again, this notion of abstraction and reusability with respect to a data source such as an SQL database, a Microsoft Access database, highly unlikely, but maybe, or any of the other type of databases where we talked about, NoSQL, such as MongoDB, for example. Have an interface that abstracts the details about how to interact with that database, such as username and password and things like that. Have an interface where another component can just say, I want to go access this data, and don't require them to enter in a username and password and other things about the database connection and all those details. Abstract that information from the other components wanting to access those things, so that that data source component just handles what it needs to do, it does what it needs to do, and has an API so that other components, maybe more business level components, can reach down and access that data without knowing all those details. Hope that makes sense. Another pattern is a presentation pattern. And I don't have it written on this slide, but there's a very, very popular pattern called Model View Controller. And I'm not going to get into the details of what that means. Basically what it means is separate domain logic, stuff about your business, the data source, and other things like that from how things are actually displayed to a user. So that what that does is, you have this component that's specifically responsible for a display, and then you can do all sorts of nifty things in there without having to negotiate around business logic or data source logic or anything like that. It's just responsible for rendering stuff to the end user. And so that's basically, the overarching theme with respect to these patterns is separation of concerns. Separate different forms of logic so that you can focus on those pieces of logic. And then the whole hopefully becomes greater than the sum of its parts when you integrate it. And so I'll say it again, I'll hammer it home. The holy grail of software development is reusability, which is simply a way for software developers to write code that can be used throughout the program. Think about how many times, if you wrote a component that was responsible for just data access, and you have a big web application or database application, think about how many times that component is going to be used. Anytime you want to read or write data to a database, anytime you want to fetch information or give something to a user, that component becomes pervasive throughout the software application. So you want to focus on that component, make it reusable and rock solid so that it can be reused. So let's talk about programming with respect to software development. So there's another term, it's also called coding. Some people call it software engineering. There's a couple different terms there. But good code needs to read like structured English. So essentially, software development or programming takes a computing problem that usually originates from a business problem and turns it into an executable program. It involves analysis, understanding, and being able to generically solve problems that result in, hopefully, reusable code. And the act of programming also involves testing, debugging, and maintaining source code. So let's go over these bullets once again, real quick. Good code is nothing more than structured English. It's English with a specific syntax. In a lot of languages you have semicolons as opposed to periods to denoting the end of a line or a sentence. You have keywords that that act as commands for what you want the computer to do. But ultimately, it originates from a business problem, and then you have to it becomes up to the analysts and engineers to take those business problems and realize how they're going to be solved using software or enabled using software, or solutions are going to be enabled using software. So you have to be able to analyze, understand, and be able to solve, and generically solve business problems. And you have to be able to solve them generically. And I use that word generically because that relates directly to the idea of reusability. It's like, okay, I can solve this specific problem as it relates to the business, or I can develop a number of components so that when new problems come along, I can just glue together these components and not have to write something completely new from scratch. Once again, reusability is just really the grail of how to do good software development. And then also testing, debugging, and maintaining it. You have to be able to do that very well. And so the last bullet point here is that software code really is just a series of algorithms. And algorithms is a very complex word, which just means a step-by-step procedure. And that's it. So let's look at some characteristics of software development. Good software makes use of patterns, just like those patterns that I gave examples of in, I think, 2 slides ago. Patterns take software development from an art or craft and make it into more of an engineering discipline. And so, many times software developers feel like, what they're doing is artistic, But then there's also a group that feels like what they are doing is really more related to an engineering practice, where they have best practices, many times patterns, and they employ those as it relates to a business problem, much like mechanical engineering or electrical engineering. But what's also interesting is that in the US, there's no certification or license to be called a software engineer. Anybody who's a coder is technically a software engineer. So, eventually this will change, but other countries such as Canada and a lot of countries in Europe, have actual certifications to be called a software engineer. You're kind of, if you've ever seen other engineers, electrical engineers, they're kind of licensed, bonded, and insured. We don't have that for software engineers in the United States, but they do have it in a number of different countries. And what I believe is that it's because software engineering is a very young discipline compared to electrical and mechanical engineering. But this will happen very soon, so that there will be some certification criteria, perhaps boards or something that maybe the state of California would have to certify people as software engineers. And I think that would really make the practice more mature and less of an art form. So good software usually has the following characteristics. Reliability, right? How often are the results of the program correct? Robustness, how well does a program manage errors, user errors or bugs? Usability, how easy is it for you and I, the end users, to use? How portable is it? How independent is the software from computer hardware? Can we move it from a Windows operating system to a Mac operating system with relative ease? How maintainable is it? How easy is it to modify? And we talked about some of those techniques, with regard to separation of concerns and layering and abstraction to make things reusable, which ultimately also makes it more easily to modify. And so, how acceptable is or efficient does it perform? How does it consume resources? How long does the software application take to return results? These are questions which ultimately manifest themselves as measurements when testing and debugging software. And that's part of the very complex and laborious process of getting good software into the marketplace or into the hands of your end users. So now let's take a look at, a very high level look at development languages. And I'm just going to list them here, and we're not going to talk too much about them. I'm going to give you some differences between the two, or between those in the list, but not too many. And because there's also many other languages. And so, some of the more widely used languages that you see are C and C++, which we don't necessarily teach in our department, in the Information Systems Department, but we do teach C#, a little bit of Java, and I believe we're starting to teach things like Python and Ruby. There's also languages such as Objective-C, which is usually Mac specific. A lot of the interfaces that you see on Mac OS X, or native Mac OS X applications, are written in Objective-C. And then there's JavaScript, which is mostly a web language, but increasingly people are finding ways to use JavaScript for more desktop or offline applications. For example, if any of you use the Chrome browser, that entire thing is written in JavaScript. The entire browser, the settings, the tabs, the interface, it's all written using backend JavaScript. And Google wrote a backend JavaScript engine called V8, and a lot of people are starting to adopt the web version of that, which is called Node.js. It's Node.js, and is really changing a lot of the ways that web development is done, and is very interesting. And I'm really hopeful that the Information Systems Department will be offering a course in how to write Node.js web applications in the very near future. We're working pretty hard on that. So some other languages that are related to the web, or another languages that are related to the web, and probably the most widely used web language is PHP. A lot of times you may hear the term LAMP stack, which stands for Linux, Apache, the web server, MySQL, a database server, and PHP. For example, Facebook for many years was exclusively a LAMP stack application written predominantly in PHP, and they even helped to revise a lot of the language specifications and compilers or interpreters for PHP. And then I have two other languages here, which are functional programming languages, which are basically languages that rely on the credibility and criteria of more mathematical applications to do their work. And functional languages are also finding an increased presence on the web, and specifically with respect to back-end web applications. So there's many others. And like I said, languages can be geared towards procedural or functional programming paradigms. So now let's go to the next slide and talk about what it means to have an application programming interface. So this is the slide that I've been alluding to during a lot of this presentation, as it's one of the underlying components that kind of cross-cuts all of these slides where I'm talking about system software and application software and utilities and device drivers. Application programming interfaces exist on all levels. And so good programming makes extensive use of this term, layering, or abstraction and reusability. I mean, just think of those terms as a group together and understand what each of them mean. So an API is an abstraction layer. It's a way to conceal the details of something while offering a standard interface to interact with it. It's simply a protocol for interaction with something kind of at a quote-unquote lower level. I gave the example of a device driver. That's a great example. And so I kind of tried to give you an example that simulates something like an API in everyday life. In everyday life we do have similar things. So we have protocols and kind of social contracts for how we do things in our worlds, right? For example, we have a common way of ordering our favorite Starbucks drink without knowing all the details of exactly how it's made. So I went on to, I think, the Huffington Post, and I found an article, funnily enough, or interestingly enough, called the most obnoxious drinks you can order at Starbucks. And so I found one, and this was really good. And it was, I would like a triple venti, half-sweet, non-fat, half-calf caramel macchiato. So think of that as a way of communicating with a programming interface in a way. You are giving a set of commands to a lower level interface, and I don't want to say people at Starbucks are lower level. I think you understand what I'm saying. To an interface, the people who work there, who then take that order and they do something with it. And when you go over to the counter where you receive your drinks, you get your drink how you wanted it. Most of the time, you get what you intended. And so that's kind of a real-world example of thinking about how application programming interfaces work. It's like a series of contracts, between components. And components, and the component that's a user of that contract, they give it parameter. They give the thing they're requesting parameters, and they do it via the terms of that contract. And then that component then goes and executes the terms of that contract. So I've stated this over and over again, but an API can be on many levels. It can be between hardware and software. It can be between device drivers and hardware. There can be system software and application software. It can be between application software and an application platform. So effectively what that's saying is there's an interface between hardware and software. There's an interface between a device driver and the actual hardware. There's an interface between system software and application software. And there's an interface or way you interact with with application software with respect to an application platform. So let's talk a little bit more about APIs. Let's go on to the next slide that talks about compiling software code and what that actually means to take code from structured English, the logic that you give it, to machine code, to something that's executable. And so that's what compiling software does. Transform source code into machine code. It creates an executable version of the code. For example, something that you can double click and actually run. And so let's talk a little bit about the simple structure of a compiler and what the compiler actually does, because it kind of does a number of things that are very useful to a software developer. So simple structure of compiler, you have the front end, which verifies the syntax. That structured English you gave it, did you do it properly? Did you misspell something? Did you misspell a keyword? Did you put a parameter into a function that wasn't intended to be there, that's outside the boundaries of what it knows to accept? That's the front end. Then there's the middle end, which performs optimizations. Did you write a part of the code that can never be executed, for example? The middle end will take that out. If there's a part of the code that can't be executed, then it has no business being in the executable. So the middle end will optimize your code and take that stuff out of there. And then there's the back end, which is the part that's actually responsible for generating the actual machine level code that can be executed. And so a lot of times, if you have any friends in computer science, a very common exercise is they'll have to write a compiler. And many times what they're writing is the back end part. So let's take a look at tools for software development. And I have a picture of a software development tool, and I believe this is the Eclipse application, which is very, very widely used. Eclipse kind of acts as a framework where it can work in multiple environments and program towards multiple operating systems. It's very, very flexible, so that people don't have to acquire a new set of skills related to the software development tool when they switch languages. They can have a common interface. Because one of the things that's really fascinating about software development is that probably 60% of it is knowing how to use the tools in your integrated development environment. So, software application, a development environment, is a software application that provides comprehensive facilities for software development. It includes a source code editor that highlights keywords, gives you intelligent code completion, the same way in Microsoft Word when you're typing a word and it gives you a little tag to maybe select the down arrow and hit enter and you'll get that word to type out for you. The same thing happens in code, and quite honestly, I think a lot of that intelligent completion idea came from software development tools. They just decided to put those into everyday text editors. It also helps you enter code correctly. It underlines something and lets you know before you go and compile and are trying to run your program whether or not you've done something incorrectly. It also has a debugger, and many times these debuggers, like I was just saying, can kind of be working in the background. So it helps to test and find bugs, to debug, and also can help you do things like line-by-line execution. Effectively, code is procedural. So you can, with these sophisticated development tools, you can run through your code, each line of your code, and see whether or not the effects that you intended actually happened. It also allows you to put in what's referred to as a breakpoint. You can, instead of just starting from line 1 and going to line X, you can tell it to run until it gets to a particular line. Then it'll stop there, give you a status of where everything's at. For example, what does memory look like? And some will actually even allow you to modify the program state and continue on. And there's a number of reasons you might want to do that. Let's say you don't want to stop the execution of the program. You just want to modify a variable because you did something that wasn't intended. And then you can continue on with the rest of the program to see if the rest works. So they're actually very, very useful. Integrated development environments are very, very useful to have. And it really makes software development a lot easier to do when you know what's going on under the hood. You know what your memory looks like and everything else that's going on. Really helps you do things a lot faster. So now, let's take a look at, and this is the last kind of module within this presentation, let's take a look at software testing and what that actually means. So software testing is simply an investigation that provides information about the quality of the software, helps you find bugs, and provides an objective view of the performance and accuracy of the software. Usually the program is executed given a set of test cases, And these test cases can be programmatic in nature or related to end user actions. So let's take a look at types of software testing. The first type is static testing, a review, walkthrough, or inspection of the software. Another one is dynamic testing, where the program is actually executed under a given set of test cases. Dynamic testing is what you usually find with respect to testing and quality assurance. There's a set of test cases, and people want to know the outputs of them. So within the idea of that, of dynamic testing, is the notion of black box testing, which examines functionality without any knowledge of internal implementation. So what that basically means is your program is a black box, and your tests are just looking at the inputs and outputs of those black boxes. And so in contrast to black box testing is white box testing, where the internal workings of the program are actually tested. So now, since we've talked about types of software testing, let's kind of look at this from another angle and talk about different levels of software testing. So, unit testing is one particular level of software testing, and basically what this means is that it only tests what we refer to as software units, or very, very small chunks of software. Another is functional testing, where you're only testing the more end-user related functions of the software. So it's a little bit more like black box testing. You also have integration testing, where you're integrating all of your components together and looking at the outputs of what happens when everything is hooked up. Then you also have system testing, which basically means that you're testing it against a variety of different types of operating systems and operating environments. And then lastly, you have user acceptance testing, which is simply what matters in this case is what the user says. Does it satisfy the user requirements? And it doesn't matter what happened during your unit test, your functional test, your integration test, your system test. If the user doesn't approve, then you've ultimately failed the test. So let's take a look at test-driven development and what that means, where this is a particular form of how software engineers engage in testing. And so basically what happens is a developer writes his test first and then writes the code to make it pass. So test-driven development essentially takes the following steps. Write a test that will initially fail because you haven't written anything to make it pass, and then you automate the test case or this test by putting into some automation environment to ensure that the test will actually be run when things are integrated. And then what you do is you produce the minimum amount of code needed to make the test pass. So it encourages you to write a minimum amount of code. And then the fourth thing is that you refactor the code to make it meet any acceptable coding standards. And it's very possible that you could have been doing that all along. So like I've said, test-driven development encourages software developers to write a minimum amount of code and to have sufficient code coverage. And what this means is to have tests that cover a majority or all of the code. However, this takes a very significant amount of time and requires a huge shift from conventional software development methods. So, it's a paradigm shift. It's a different way of thinking. But I've actually been engaged in this practice and I found it very productive, as a lot of times what happens, and we'll talk about this notion when we talk about systems analysis and design, is that many times after code is developed, there's in theory a phase where you go through quality assurance testing. And there's an interplay between additional development, finding bugs, and the quality assurance phase that can sometimes take a really, really long time. Test-driven development, I've seen it cut down that quality assurance phase, or that maintenance phase, extraordinarily. It's really been very effective, and so I think it's a valuable thing to help you guys understand how software engineers or developers can work in a test-driven development fashion to minimize the amount of QA time that has to be spent when developing an application. So in conclusion, there are many different types of software that serve different functions, and we talked about a few of them: system software, application software, utilities, and then within them we talked about device drivers, operating systems, etc. And there are many different ways to maintain and release software. There's also a number of languages and methodologies developed in test software, and we talked about a bunch of those. And so I guess I just want to hammer home the point that this is really just the tip of the iceberg that we're talking about with respect to very intricate levels of software development processes and how people actually go about the act of creating a lot of the applications, wonderful applications we've come to enjoy. And so software development is not just for computer science majors. A lot of you may be thinking that you need a computer science background to do this. I don't know, you may be. But the reality is that very little of what is learned in computer science actually prepares you for a career in software engineering. And so IS, doesn't prepare you exactly to be a great software engineer, but I think what it does, especially what we do here at San Francisco State, is particularly valuable as we teach a number of different programming courses, and we teach you to be a good evaluator of business problems and to be able to translate those problems into things that can be enabled by technology. So that's all I have for today for this particular class presentation. I hope you enjoy it. It was pretty intricate with respect to software engineering, but there's really a lot there. And so what I tried to give you guys was a high-level overview. So make sure you contact me with any questions. I'll be more than happy to answer from you. So I'll see you this week.